Welcome, everyone, to our ABI online seminar, Rethinking Electronics for a More Resilient, Renewable Future. Quick introduction, I'm Ben Sanderson. I'm a marketing coordinator at ABI Electronics. In terms of how today's session is going to be structured, you'll first hear from our international sales manager, William Santos, who has over 25 years experience working with SMEs and international companies, developing in-house testing, maintenance, repair, and obsolescence mitigation strategies for critical electronics. His work has saved millions of pounds in recouped maintenance and repair costs for the industries that you can see here. He'll be providing a presentation on the current nature of electronics within the renewable energy sector and some of the strategies that can be implemented to help mitigate some of the challenges that you might be facing with your industrial electronics. After this, you will hear from our business development engineer, Jake Butler, who also has a wealth of experience with electronics, including hands-on expertise in manufacturing and testing PCBs. He'll be providing a live demonstration of our flagship product and some of the testing procedures, systems that the Boardmaster can provide and how they can help with your repair strategies. So without further ado, I will pass you over to William.
Thank you, Ben, for the introduction. And yeah, another big welcome from my side here to everyone joining us today. If you're joining in the evening or in the afternoon or in the morning, we have people from Canada, from the US, Latin America, all the way to the Far East joining us today. So thank you very much for joining us. I'm just going to go through the agenda. We're going to be starting by discussing the role of electronics in renewable industry, the operational, financial, and sustainability challenges created by the dependency on these complex systems. Should we move away from calling them minor components, which is obviously the known terminology for electronics in renewable energy? We're going to be discussing circularity and obsolescence management as well. What are ABI Electronics and the Repair Don't Waste movement all about? So we're going to be learning more about our organization and our global sustainability movement. We have a case study as well, based on GE, the partnership that we have established with GE a few years ago. And my colleague, Jake Butler, as Ben mentioned, he's going to be going through ABI's flagship product, the Boardmaster, and explaining how renewable energy companies are using our systems to diagnose, repair, and reuse electronic circuit boards. So the industry has gone through profound transformations over the last 20 years or so, where we're seeing more and more complex systems playing a vital role in how clean energy is generated in the wind sector as well as the solar energy sector. A recurring theme that we see in these two sectors is that the majority of people responsible for asset management policies, they don't really understand how these systems work. And they don't know. They come to us and say, right, where electronics are used in our turbines, because obviously they are known, they are classified as minor components. So a lot of people don't actually go looking into them. We had people working from big organizations in the renewable energy sector coming to us and saying, look, I don't actually even have access to the data. We don't know how much we're spending on electronics repair or recovering and so forth, or buying replacement parts. So here are some of the systems that are used, where you would normally find electronics, controlling them and really taking on all the different inputs from different sensors, from the gearbox, obviously sensors looking into air speed, blade speed, and so forth. And then all this is basically done by electronic circuit boards. And they are, again, complex, they are expensive, as you're going to be seeing in the next few slides. Now, when it comes to solar energy, there are multiple systems as well, controlled by electronics, from sun tracking devices to obviously the popular inverters. We have the IGBT solutions as well, being triggered by IGBT controller boards again. And if the controller board goes, obviously the IGBTs will go. Not only have an expensive circuit board to fix, but now you need to find expensive IGBTs to replace as well. And there are many different electronics being used currently across the industry. And we really need to have a think about how we can manage them better in a more sustainable manner. Now, because there are so many systems that rely on circuit boards to operate, obviously in themselves represent huge challenges. Supply chain challenges, obsolescence as well is a massive issue. And if you don't manage these challenges properly, your company's profitability will be affected. As I mentioned, these are complex systems. They have been designed by one company and then eventually assembled by someone else and then finished off by a third party. And then eventually they could be running on your machines in Africa, in North America, for instance. This fragmentation in our industry doesn't help much when it comes to understanding and mitigating some of these challenges. But they are designed obviously to last many years, but the components in them, they fail and they age, they can obviously stop functioning properly. And if one device stops functioning properly, you could have a chain of events. So they are subject to lots of harsh environments. Things can go haywire and it could affect the electronics. And as an operation manager, operation director, you need to be thinking about, if something happens, what we're going to do, how we're going to be resolving the issue as quickly as possible in a sustainable manner. Financial challenges. As I mentioned, each wind turbine requires between 20 and 30 circuit boards to operate, and they are costly. They are valued between 3,000 euros to 5,000 euros. But you could take 3,000 euros as an average, and then obviously if you multiply that by the number of PCBs that are required to operate a wind turbine, we can run into the tens of thousands per machine. And again, similar situation in the solar energy, with the solar inverters. A solar power plant could have hundreds of inverters and they all have those systems built into them. But now, if we look into the number of turbines Vestas has in operation currently, 56,000 wind turbines globally in operation, we're now running into the billions of euros invested in electronics assets that obviously they need to last, they need to be kept in operation so that we can extract the most value from them. And obviously, because of the fragmentation that I mentioned before, the cost of the spare parts, especially in the last few years, I've seen a massive increase. Actually, the cost of a circuit board that was before 1,000, now 3, now is 10. So we have also seen a massive increase in the last few years in the cost of spare parts. We also have sustainability challenges, and the industry is under pressure, not just to return to profitability, but also to demonstrate that they are really committed to the environment, really committed to sustainability. And you can't really call yourself a green energy company if you are producing e-waste, can you? So that's something that obviously people need to have a think about. If your maintenance strategy is based on just replacing replacing circuit boards and getting a new one every time that something, just one capacitor, one pennyworth part fails, not only you are missing opportunities to learn why this electronic is failing and how you can prevent that failure from happening again, you are adding to the fastest waste stream, the fastest growing waste stream currently, which is e-waste. So we need to do better as an industry to expand service life of electronics. As I said, they are designed to last many years. Each PCB can be reworked up to 4 times before it has to be taken out of service. And that doesn't mean throwing away. It could be now used as a donor of parts, but potentially even obsolete parts, to keep all these systems going for another 5, 6, 10 years. So wasting these precious resources is really a no-go as far as we're concerned, and I think it's obviously the industry needs to look into that. Now let's look into solutions. And the first point that I think it's important to stress is the fact that systems need to be designed for repair. They need to be designed for circularity and for sustainability. And there are many points that I could discuss here, but I have listed there some of the areas that I think the industry can do better. So I think we need to move away from bespoke designs, which obviously makes the operation and maintenance more difficult. I think we need to replace that for modular designs. We need to think about standards in terms of connectors, in terms of protocols and so forth. there needs to be an understanding that operators, asset owners, they should have access to at least the bill of materials. So they need to know which components are on their circuit boards. So if they are able to diagnose, then they know which component they should be replacing, like for like, and keeping the device running at highest value for as long as possible. Schematics, we're big advocates here about sharing schematics, circuit diagrams to help with the maintenance and repair. The firmware, can we make systems field upgradable? And these are points that we do here at ABI. Yeah, we're not just preaching here. These are core aspects of how we design our own products here at ABI and how we support our customers. So if you have any customer anywhere in the world and they have a 5-year-old system, a 10-year-old system, and they need to repair it, we don't force them to send it here. We charge them a small fortune to have the system repaired here. We first ask, are you capable of repairing circuit boards? If you are, if you want to exercise your right to repair, we're going to help you. We're going to send the list of components that you can buy locally. We can share parts of the schematic so that to help you with the troubleshooting. We can talk you through and give you instructions on how you can repair your system. So if we can do it, I think the rest of the industry, the rest of the equipment manufacturing industry can do that as well. And then obviously tap into the many positive aspects of servitization, which is something obviously potentially for another discussion. But I think you get the point. We need to do better when it comes to designing electronics and make sure that those designing those circuit boards, they are trained for repair as well. If you have a design engineer who's never repaired any electronics and you ask them to design a piece of equipment for repair, how are they going to do it? They don't even know how to start. So again, we need to bring other parts of the industry together, including academia, to help us improve the knowledge overall. Obsolescence mitigation. This is another point that if we can do better and improve how we manage obsolescence, we're going to be reducing e-waste so much. And we are part of IOM, an organization that, IOM stands for International Institute of Obsolescence Management. And I have recently been presenting on the aspect of bringing sustainability in obsolescence management and moving obsolescence management from being reactive to being proactive. And I think it's as a concept, obsolescence management needs to be embedded into product specification, manufacturing, use across all the entire life cycle, and not just be a concern when it's too late. And if you do that, if you really think about obsolescence management from the time that an asset is specified, then you're going to start collecting a lot of, important data that will help once the asset is declared obsolete. Obsolescence is a real deal, is a real concern. When I started in my career 25 years ago, something obsolete was, a piece of equipment, made 40 years prior. Yeah. 34, 35, 40 years prior. Nowadays, we're seeing complete wind farms, solar plants, rail systems, airplanes launching with a lot of their vital systems already obsolete. So if you think that obsolescence is something that is not your problems, it's someone else's problem, well, it is your problem as well. And if you want to learn more about obsolescence management, I would recommend people to find out more about IOM. So it's IOM. Search them online, and you can connect with them on LinkedIn as well. Manuela Grunzi is our contact there. She'll be more than happy to, point you in the right direction. Obviously, we are big advocates here at ABI for the repair of electronics as being one of the solutions. So it's design, it's obsolescence management, repair, recovery, reuse, before recycling, or we even think about recycling circuit boards. And then what do you stand to gain from moving away from replacing circuit boards to now repairing and reusing them? I have listed there some of the key aspects, and one of them obviously become more independent. You can mitigate some of the issues that I mentioned before much more effectively compared to if you are just relying on third parties, relying on supply chain. If you're delegating your maintenance strategy to a supply chain, and if you let supply chain regulate the pricing, you're not going to be never in control, and it's going to be very difficult to become a profitable operation by doing that. You can limit exposure to cyber risks. In one of these slides, I think I forgot to mention, but you may have seen on LinkedIn, we published a report on this recently based on a piece that was published by Reuters. So they conducted an investigation and found that some Chinese inverters had some rogue components fitted to them, which were capable of being called from home, called remotely, basically controlled remotely, and entire operations could be switched off. So now we don't know if the rogue components were there from start, or if they were infiltrated when something went back to the manufacturer for repair and maintenance and then came back with these extra devices. But it is a real risk. Yeah. We have other issues. We have tariffs. We're all seeing what's happening around the world today. If you are, again, delegating to third parties, and if you are just, not really developing a strategy closer to home, then you could be exposed to, different issues like that. We're talking about reducing inventory, becoming more agile, becoming leaner, which is incredibly important as well, and ultimately more profitable and more sustainable. Repaired PCB saves about 90% of the cost, reduces 85% fewer emissions compared to buying new. So not only have the operational benefits, we also have obviously the financial benefits as well as the environmental issues as well, or environmental benefits as well. Now, for those who are not familiar with ABI, ABI was started in 1983, and we're big enablers of repair across multiple industries. We cover over 20 different sectors of the industry, from defense and aerospace to automotive, rail transport, semiconductor manufacturing, biomedical. So these sectors rely on our systems and implement our hardware, software products, and our training to maintain, repair, recover, reuse their electronic systems. So we don't repair. We're not involved in repairing PCBs. We can't help you with that, but we can supply the equipment and help you overcome these challenges by yourself within your organization, utilizing, as you can see the picture there, the board master, which my colleague Jake is going to explain, is like an all-in-one solution, universal solution that can diagnose faults down to IC level, and Jake's going to explain a bit more later. We're also the founding organization behind Repair Don't Waste, which is a project that we are very proud of. So Repair Don't Waste started as a hashtag in 2015, became a community. The community became a movement. We currently have over 150 global brands that are supporting the growth of Repair Don't Waste. The movement exists to draw the attention from business leaders to the importance of developing in-house capabilities for repair and maintenance of critical assets. Okay, we have a website, repairdontwaste.com. A lot of information there. We have articles, case studies. We have information about standards, IPC standards that you should be training our technicians on. We have recently added a new webpage in repairdontwaste.com/learn. There is a workstation page where you can see our recommendation for what should you have in your lab, in your repair facility, because sometimes people don't know how to start or where to start, which equipment they need. So you can go to repairdontwaste.com and learn more about that. And we're very proud to have achieved national recognition here in the UK last year, and being awarded Sustainability Champion by Engineering Matters about a year ago. Now, I just want to bring your attention to a case study before my part is finished and Jake can start, which is based on our partnership with GE. Now, GE, up until 2018, they were not repairing any electronics, no circuit boards from the wind turbines. They were basically just replacing them. Now, we started a pilot project with GE in Brazil, in the northeast of Brazil, where they had a very good technician who had been repairing without anyone telling him to. He was just like, I'm sick and tired of seeing a lot of PCBs just mounting up and nobody doing anything. We can't just throw away these PCBs because they are worth a lot of money. So he started using traditional instrumentation to do some testing and repair some of these PCBs. And he created so much value that the Latin American operational director took notice and said, right, so we're going to be investing in you, trying to create like a pilot program. What do you need? What would you like to have in your lab? And he said, well, can I ask for a board master? So that's my dream equipment. And the director, approved the investment. Long story short, the system was implemented in Brazil, and then GE rolled that solution out to 8 locations across the world to date. And in 4 years, this operation saved GE over $20 million. Now, this came from them being able to diagnose and repair very quickly, especially during the pandemic when we had shortages and some spare parts were on a very long lead time. So they managed to repair those very quickly. Not only they started repairing more and more of their own equipment, but they can also repair third-party equipment. So there's a lot of money in wind or solar plant operation and maintenance, which implies being capable of successfully manage, maintain, operate third-party equipment with no schematics, with no information from and no cooperation from the original manufacturer. So they have been really, successful in using our systems and in bringing repairs in-house. But we have, many other customers working with us in this industry. We have in the solar energy sector, we have Plenium. In Spain, we have Siemens Gamesa, Boralex, EDF. All these companies there listed are some of those that are using our systems to maintain, repair, reuse critical components in the energy generation sector. Okay, so that's my part done. I'll be around helping clarifying some of the potential questions that are being posted on the Q&A. But without further ado, I'd like to pass this over to Jake. Jake, the floor is yours. Thank you.
Thank you very much for that introduction, William. As William mentioned, my name is Jake Butler. I'm a business development engineer with ABI Electronics, and thank you for taking the time to join us today. So as William's mentioned, I am just going to take you through a demonstration of the Boardmaster and also our System 8 Ultima software, just by covering some of the key points for the correct standard of repairs. So inside this test flow, we've got all different aspects of testing, and I'm just going to go through a quick repair flowchart that we've generated around feedback from our customers. So on the screen now, you should see what says workflow, and this just mentions some of the key steps that we should follow in order to carry out repairs to the correct standard. So the first thing what we should be doing with these boards is the visual inspection, so having a physical look over the PCB for any defects. Once we've covered the visual inspection, we will go into power off troubleshooting. So this is a safe, non-destructive testing method, which is not going to cause any more damage to the boards if you do power it up and there is an underlying issue there. We can do that through PCB level, so that would be through the edge connectors themselves, and it's going to give us a full fault coverage of the PCB. So it's a great way of understanding if there is an issue on the board and also how to locate it a little bit further. Once we've done the PCB level, we will then go into component level. So once we know where the fault is on the board, we will then go testing all the different components in that area to work out accurately where the fault is. Everything that I'm mentioning here, we are doing in circuit. So we're not going to be removing any components from the circuit. That can be a great concern, obviously causing more stress to the board. And quite frankly, it's not something that is necessary to do, removing components in order to test them. Once we've done with the power off section, we know the board is safe to power up. What we will then do is we'll power up the PCB, but before going to the PCB level or to the component level, as we did with the power off testing, we're going to check the power consumption just to make sure that the right voltage is being inputted, that we've got the correct power, etc. Once we've checked that, we will then do a functional test of the PCB itself. So testing the entire board, just making sure that there's no faults, that it's running functionally okay. If any faults are picked up, we can then jump into the component level to work out where the fault is on the board. Once obviously them steps have been completed, if you do find a fault at any point, we will then stop, we will then replace, retest, ultimately at that same point, just to see if those issues have cleared. While we're doing this, a comprehensive report will be generated, and I will give you a good example of that later on. So let's jump into the test flow itself. So what a test flow is, just to give you a quick introduction, it is more of a interactive test procedure. That's the best way I like to call it, just because you have all the normal information you would have from a test procedure, but you also have added benefits as well, which is going to help with the troubleshooting time, the ease of diagnostics as well. The reason for this is that you're going to be able to save all of the information as you normally would, so instructions, pictures, videos, anything to aid the engineer or the technician to do the test. But you're also going to be able to save additional information. So that is settings, what you need for each instrument. So they will be preloaded as we go through. You can also save the masks, the results from all the different tests as well. And as I mentioned earlier, a comprehensive report will be generated at the end of the test flow, which will give you all the information you've done throughout the test flow. So let me move into the first step. So the first step that we have is what we call a menu. So as you can see here, we do have an Enercom controller board on the screen. And as you can see, we have a lot of different buttons on the screen. So you see visual inspection at the top, power analysis. What these are hyperlinks to different steps inside of a test flow. So if you have a board and you know the issue is with the 7400, for example, instead of running through the entire PCB, what you can do is you can use these hyperlinks to go to that specific step inside of a test flow. And it's just going to make it so you don't have to do any unnecessary testing, especially if you know where the issue is. Obviously, for the purpose of this demonstration, I will just be going through the whole entire test flow, but it's just some relevant information for you. So the first step that we are going to carry out, as we mentioned on our repair flowchart, is the visual inspection. So this is going to be visually looking at all aspects of the board and just making sure there's no underlying issues. As I mentioned, we can include information what is going to help the user in order to work out what these issues are. If I go to this menu on the right hand side and press instructions, it will bring up test instructions. So for the visual inspection, we've added a lot of information, such as what we should be looking for. So as you can see here, burnt components, we have broken traces, and we also have bad solder joints as well. These are the key things you want to look for the visual inspection. And obviously, if you see any issues, it's important to get them rectified before moving further. With my board, I can't see any issues. So what I'm going to do is I'm going to go ahead and press yes as it passes the visual inspection. And as you can see, it then tells me pass, please continue. So the next thing that we're going to do is we're going to test the entire board under power off conditions. So for this, I'm going to plug into our dedicated power off module called the AMS. And what this is going to allow me to do is this is going to allow me to plug into the edge connectors under power off conditions, just to make sure there isn't any faults, say for example, when we turn the board on under power on conditions. So with the power off testing, there is two different types of testing. So the first one is what we call the 3dVi testing, which requires a ground reference. I will explain in a short second why that is. And we also have another method called matrix. Just for this very second, I am just going to focus more on the 3dVi. So how this testing works is it tests every pin on the edge connector, and it's going to test it to the ground reference that we have placed on the board. So this is going to measure to see if there is any issues with components on the board. As you can see from the test here, it is something where we have picked up a fault. So if I just scroll down, you'll be able to see these signals here. Channel 35 and channel 37. So if we go ahead and press onto here, you'll notice that we see on the screen, if you know a little bit more about VI or curve tracing as it's called as well, you'll notice that we see kind of a diode on the screen. But in the signal itself, it's something where we just see a resistor. So when we're looking at this signal, it is something where we could work out that the issue with this is a diode. And then similar to the other pin as well, we see a resistor. We also see a resistor on the screen, but not on the same resistance. So that means that another resistor could have failed, and it's going to be able to help you pinpoint where the issue is on the PCB. This is why power off testing is a great tool to have. So let's move into the other testing type. So this is what we call matrix VI. So this works in a similar way to 3dVi, but instead of testing to the ground reference, we're going to test each pin against every pin. So this means for pin 1, we're going to test it against pin 1, pin 2, pin 3, all the way up to pin 42, just because that's the amount of pins I have. And then when we go through, we're going to go to pin 2, and we're going to do exactly the same testing type. So this is going to give you full fault coverage through the edge connector, so testing to the ground reference, so testing the components around the edge connector, and using this one to test the edge connector itself and the different connections. So let me go ahead and press start, and we'll start running through all these different tests. And as you can see already, we are picking up a few faults, but we're not getting a red on the right hand side. So sometimes we do have the allowance to have a few pins fail, but it's important that you go through each of the pins and analyze the results just to make sure there isn't any underlying issues. As you can see here from pin 2, if we look at pin 224, you'll notice we can see kind of a resistor, but when we look on the screen, we have a capacitor on the signal. So this means that there is a fault there, and most probably we'll need to do further investigation. Right, so let's go ahead and let's just go back to the repair flow chart. So the next thing that we need to do, because we have found the fault at PCB level, is now we need to go down into component level. So what we're going to use is we're going to use the same tools that we had previously. So we're going to use the AMS, we're going to use the 3D VI tester, and also the matrix VI. But this time we're going to be able to test using the ICs themselves. So we're going to be able to test the IC just to make sure that there isn't any issues there. So we're going to do a similar thing as we did with the edge connector. We're going to plug into the AMS and then plug onto the PCB. As we mentioned earlier, it's important to have that ground reference because with this test, we're not testing the IC itself, but more we're just testing the components on the path to ground. So this can include diodes, resistors, capacitors, similar to what you've seen with the edge connectors. So if I go in and I go and press start, you'll see that the test is starting to run through. And I'm not seeing any particular issues here. So that means that the issue isn't outside of the device if this component did fail on the edge connector itself. So now we can do the same on the matrix VI. So if I go ahead and remove my ground reference on the PCB, it's something I can then plug this onto the other component. So this is an LM324 this time. As you can see with this, it doesn't really matter too much about the component itself. All it really cares about is the connections inside of the component. So as you can see, when we start running through, you'll notice that the signals on this one do look quite different compared to the signals that we've seen. If we look at pin 1 reference 13, you'll see that we have a number of components interlined here inside of the component. But with this being a comparison method, it's a great way of not really having the full understanding of the board, but being able to fully test it against the golden reference, just to make sure that there isn't any issues on the PCB itself. What we can also do, as you've seen here, we've tested through the edge connector and we can also test through the ICs themselves, but we can also go into component level as well. One thing that you've probably thought is, why is the 3D VI tool called 3D VI? All we've seen currently at the minute is 2D tests. Well, if I go into the capacitor, you'll notice that we have a different looking kind of signal here. The reason for this is that we've added a third axis. Anyone who's played with 3D VI before or curve tracing knows that typically it is a voltage being plotted against a current. With the 3D, this is good for your frequency dependent components to be able to test them fully. What I mean by that is we can test all the different frequencies between a specific point which is set by the user in order to fully understand what's happening at that particular frequency. So as you can see here, I've now got my 3D signal and my 2D signal on the screen. And if I use this bottom scroll bar, I can actually view it at different points inside of the frequency. If we look at the bar at the bottom, this highlights which frequency we're currently at and ultimately what it looks like. As you can see, we've currently got the mask at the minute, but when I go ahead and start testing the component itself, you'll notice that we have a orange signal which appears, and then we can follow that between all of the different frequencies. With this test, we are just running at a little bit lower frequency, so it is just going to take a little bit longer to run, but we'll see when it comes through as it will highlight whether it has passed or failed. As you can see, we have got a failure here, and it looks like we have a little bit of a leaky capacitor on this particular point. As you can see, the signal is not matching the mask which has been previously stored, and as we start looking at all the different frequencies, you'll notice that it's still keeping that same leaky capacitor look, and ultimately it's indicating that there is a failure here. So what we would do is we would send this board off to the engineering team in order to be analyzed further and ultimately replace this component due to the different kind of signals which is being produced.
And if I may just make a quick comment here, Jake, I think that's a good illustration of something that happens in the real world. which is component degradation. So when components eventually degrade because of age and because of they've been in use for a long time, they could obviously change their characteristics, which could potentially implicate in a fault, at system level. So this test will definitely help locate those devices, but also if you have good data and if you observe your asset during its life cycle, you will be able to predict when devices are likely to fail. So we can provide all the data for you to run a predictive testing strategy, moving away from just being focused on correcting faults, but also preventing faults from happening in the first place.
So now that we've tested our discrete components, what we're going to do now is we're going to move into the power on side. So we've looked at the PCB under power off conditions. We found the faults with the edge connector and also with the components themselves. Ideally, in this case, what we would do is we would retest all the tests what we've done after replacing the components. But for this demonstration, we are just going to move straight into the power on section. So what we're able to do now is we're able to power up the board and test the power connector. So what we're going to do is we're going to analyze what power is being inputted through our power cable just to make sure it is what we expect here. So as you can see, we can measure a range of different things. So we can measure the power, the voltage, and the current, depending what's most important for you. But all we need to do for this particular step is switch on the power supply. And as you can see, it will analyze either, like I said, the power, the voltage, or the current being produced. And as you can see, we have all passes. So we know that our PCB is safe to be powered up with the voltages what are being inputted. Ultimately, if this was a fail, we would turn off the power supply and make sure that no unnecessary damage is being caused by keeping the power on for too long. So now what we're going to do is we're going to move into testing through the edge connector itself. So for this, we are able to do two different steps. The first step, what we're going to do is we're going to test it through what we call the advanced board checker. You're probably thinking, what is the advanced board checker? But the best way to put this to you is that this is going to be testing the edge connector functionally. So by doing this, we're able to either input or measure different voltages what are being produced by the edge connector itself, and it's just going to give us a full overview as what is happening with the PCB. One thing that you're probably thinking, especially by seeing the edge connector on the power off and also power on, is what happens if I don't have access to a schematic? This isn't the first time that we've had this question. It's not the last time either. But ultimately what you need to do in this side is try and get the schematics. At ABI, we do have a good solution for that, which is called Revenge. It is our reverse engineering tool, and it's going to be able to reverse engineer any kind of PCB where you don't have the schematic. So you can use this for the troubleshooting side. If you do want more information, feel free to contact us after the session, and we'll be able to provide you more information. So as you can see on the screen, we are currently testing through the edge connector, whether we're driving or measuring signals, and you can see that we have a green tick which is indicating the pass. So we know that the PCB is working functionally okay. What we can also do is we can also test all of the connections from the edge connector. So with this, we're just simply inputting and measuring the voltages. But what we can also do is check the connections. So if there's any shorts, any open circuits, we can see any connections what aren't supposed to be there by comparing it to the golden reference. So let me go ahead and move into the next test. What we'll be able to do here is go ahead and press start, and it's just going to measure all the connections and compare it to our golden reference. So you can see down here, we do have a green tick on the connections and also the voltage as well. And we're able to analyze all of the connections. As you can see, we do have a note of open circuits just because they aren't physically connected. But we're also able to measure where the grounds are, where our voltage is being inputted, and if these are correct to the original standard. Now that we've tested our PCB through the edge connector itself, what we can do now is move into component testing under power on conditions. So the first thing what we're going to do is we're going to look at the different ICs on the board. So what we're going to be able to do with these under a power on condition is test it functionally. So what this means is we're going to be able to functionally test the IC. So we're going to be able to measure the truth table. So measure the 0, 0, measure the result, the 0 ones, the 1 zeros, and the 1 ones, just to make sure that it is working okay. So what I need to do for this is just plug onto my IC. So everything that we're doing here is going to be in circuit. There's no need to remove it from the circuit as I mentioned earlier, and we can just go ahead and press start, and it's just going to power up the IC. Not enough where it's going to cause any damage. We do have a safe technique for that. We do explain that more during the training, and we're just going to be able to measure whether it is working functionally okay, and also the connections and the voltage, what you saw from the edge connector as well. So what we're measuring here is digital ICs. We do also have the capabilities to do this with analog ICs as well, where it does run similar tests. So instead of a truth table test, it's called the analog trace. I'm not going to show that today just for the time, but it is just something to let you know that the capabilities are there. So one thing that I want to run into now is IGBT. So I'm just going to pass this over to William just to give you a little bit more information just while I am setting up the equipment for this.
Thanks, Jake. Yes, well, obviously IGBTs play a massive part in power generation, especially in clean energy generation. And it's a question that we get asked a lot by our customers and companies wanting to work with our systems. And IGBTs obviously can be tested using the board master, as Jake is going to show us in a moment. But also it's important to talk about the role of IGBTs. They are triggers. And because they are constantly working, constantly, in operation, they can also degrade and they can break down. They're fairly expensive parts, but something that some people fail, especially in engineering teams, they sometimes fail to appreciate is that you shouldn't just focus on the IGBTs. You should be thinking about the controller boards activating the IGBTs as well.
Thank you very much, William. So with IGBTs, I have picked 3 specific tests which we're going to show you today. The first one is going to be about the body diode. So it contains a body diode which is there to protect it against reverse withstand voltage. So what we're going to do is we're going to ramp up the voltage on the collector and the emitter until the body diode starts to conduct. Once this happens, the system is then going to produce the result and ultimately test just to make sure it is in the right specification. So for this, all I need to do is press start, and as you'll notice, this voltage on channel 2 has been ramped until we hit the current limit, and then it is going to produce the forward voltage of that diode. As you can see here, it's 0.78 and it's inside of our tolerances, so we get the pass. What we can also do is test the gate threshold voltage. So this is going to work in a similar way where we are going to ramp up the voltage, this time between the gate and the emitter, until the collector emitter starts to conduct with a low current. At that point, it's then going to record the voltage and provide the results, ultimately given as a pass or fail depending if it is inside those specifications. As you can see here, we've got a voltage of 4.5 and that is in the correct threshold, so this is given as a pass. What we can also do is test the fully on voltage. So for this, we ramp up the gate to the emitter voltage until we see a collector emitter voltage with a lot larger current. What this is going to do is it's going to give us the value of the gate voltage, and it's just going to test whether the IGBT is fully on or not. So if we go ahead and press start, we can then go ahead and see whether it passes or fails and it is inside of our specification. So as you can see here, we've got a voltage around 5 volts, which would be expected, and ultimately is given as a pass. What we're going to do now is we're going to jump away from IGBTs and more into opto. So I'm just going to pass this back to William, who's going to provide you a little bit more information about optos.
Obviously, we're going through different sets of devices and different test techniques for PCB level, for component level, power off, power on. And I think, it's important to take optocouplers into consideration as well. There are many systems out there that require those components to function properly. But the trouble that we have with optocouplers is, just like most analog devices, they age, they degrade with time, which could potentially impact the synchronization of the multiple systems associated with them. So they could potentially still be functioning, but because they are out of specification, they could get the system out of sync as well. Okay, so I think it's important to have a look and see how we can test optocouplers. We're going to be doing not just a functional test, but we're going to look into some parametric tests as well.
Thank you. So the first test that we're going to do is we're going to be testing the opto fully. So we're going to be using two different instruments here. The first one is to input a specific pattern into the opto coupler. What is then going to happen is the ohm meter is going to measure the forward voltage which is being produced, and it's going to compare it against the settings that we have saved. So for this, I just need to go ahead and press this run button, and it's going to start running the test. As you can see here, we do have a fail for this test, so which means that this opto could be showing some errors and would need to be looked into further. Some of the other tests that we have is to be able to test the opto CTR, so the current transfer ratio. So for this, we do need to plug onto the opto directly. And for this, it's just going to measure what the current transfer ratio is and see whether it is in the specific band it should be. So what we can do now is we can press onto the test. So this isn't what we call a specific instrument inside of the System 8 Ultimate software. This is done via programming, just for your information. This is something that we do show more of in the training in how to do these different tests, what are available with the Boardmaster. So as you can see, we have a current transfer ratio on channel 1 of 406 and on channel 2 of 204%. It's given us what the input is and the output, and we're able to analyze those to see if it is in that specific band. With this already being set up, as you can see, we have a pass as it is inside of our tolerances. The last one we have is about propagation delay. I am just going to pass this back to William just to give you a little bit more information.
Obviously, this is a quick reminder that we're giving you some examples of the key tests that are usually chosen and run by our renewable energy customers. But just continuing with this theme of testing optocouplers, obviously we look into the current transfer ratio. The propagation delay is just a good illustration of how age can impact an optocoupler, which doesn't mean that you should be just removing all the optocouplers that you have on the board because you are concerned that some of them have developed a propagation delay issue. We did have a customer operating in the rail industry that they were in the same dilemma, which is should we replace all of these components or try to do some more testing? And the problem that they had in real life was that the train was closing their doors, but the system was taking a long time to inform the driver. And then the driver had to step out and look at the doors, and then the doors were still were all closed. So, and then he stepped back in, and then he realized, well, the doors are indeed closed. But this delay of information was causing, big issues for that rail operator. And their first thought was, well, let's replace all of the components. Optocouplers are expensive. They also obviously become obsolete. And we should really try and minimize disturbing PCBs once they have been fielded. So we help them establish this test that Jake is going to show us in a moment, allowing them to identify just the age devices and replace them rather than having to replace 40 components, save them a lot of time and a lot of money.
So what you can see here is what we're measuring the propagation delay. So usually when you're measuring this, you would measure the input and compare it to the output. But as this is a comparison method, and we're just going to be comparing a golden reference to a faulty board, we're just able to see whether it is inside the mask. With the mask, it is fully customizable. So if it does have to be a little bit more strict, or if it can be a bit more lenient, you can set it to how you like. But ultimately, you can see when the optocoupler is activating. So we can see here it's around 7.5 microseconds, and ultimately this is inside of our mask, so it's given us a pass. As I mentioned at the beginning, once we have run all of these tests, it is something that it is going to generate a comprehensive report. So I do have a report which I already generated here just specifically for this demonstration, but you can see the kind of information that is being produced. So as you can see with the visual inspection, even though we didn't use the Boardmaster, this information is still documented onto the report. So you can see we've got a pass for that. When we scroll down with the edge connector, we can view all of the different VI signals which are being produced. We can see the mask, which is the light blue, and the signal, which is the dark blue, for all of the different pins. Same with the edge connector for the matrix as well. We can view all of the different pins, all the different tests which have been run. With this running 42 times 42, which is 1764, we can view all of the different tests inside of the report. This is something where you can pick and choose what information you want. So if you don't want these signals, just because there's too many, you can remove them from the report itself. We do show you more of that during the training. As we scroll through, we see more about our components which we've tested. And as you can see here, we're seeing a failed result. So ultimately, this is the capacitor, which I was relating to earlier. And as you can see, we can view all of the different frequencies. So we can view what it looks like after 10 hertz and see whether this is a pass or fail. And then we can scroll through all the different frequencies in order to view where that failure is. As this with this component, it isn't something where it might not fail through the entire frequency, but at a specific frequency. So you can view exactly when that is. If we scroll down, we can view information about the power analysis, so what results we was expecting and what the results were. Same with the edge connector as well. But when we scroll down, we see more information about the components that we're testing, so we can view all of the logic data, so the truth table tests, which I was relating to earlier, and also the information about the IC as well. When we scroll down, we see more information about our IGBT tests and also our opto propagation delay. What you can do is you can take a screenshot of the instrument just to see exactly where that signal is. As you can see here, we do have a pass with 100%, but you can view exactly where it is inside of the mask. And that is it from me. So I'm going to pass it back to William Santos. Thank you.
Thanks, Jake, for the brilliant presentation, and to all of you in our audience who were still there, watching this presentation. It's now just a couple of minutes over time. I just, before going to the Q&A, if you need to go, I just want to say that obviously, first of all, thank you very much for taking the time to joining us today. If you could contact us on sales@abielectronics.co.uk. If you could send us your requests for more information, perhaps for a demonstration, we'll be more than happy to help and support you and take your inquiry further. We're also available on social media, so LinkedIn, X, Instagram as well, so you can easily contact us through those means as well. Now, when it comes to Q&A, so we have some questions that have been selected here very quickly. So first of all, can the tests be automated? Can the system test multiple points at the same time? Which is a great question. Yes, the answer is yes. So obviously we showed a very Jake took his time to go through all the steps, manually. But this is one option, but you can also connect everything on a board. You can use a test rig, and then the system will be able to run tests automatically and then generate the report automatically as well. What's the typical time involved in setting up a test flow? That's another very good question. Thank you for that. And it really depends on how complex the circuit board is. Test flows, normally they start simple and then they grow over time. They can become more complex over time. So in order to put like a structure together, it doesn't take any time at all. In order to add a lot more information, perhaps videos, more instructions, PDFs and so forth, documents, it might take a bit longer or more steps as well. But, we're talking about, a few hours, let's say, and then that's, time well invested, because then this work instruction can be used and can be shared across your company sites, for instance, and get more different sites, for instance, using the same standardized work procedure. The test flow, like the one that Jake mentioned, this is your company. It becomes a company property. It belongs to your company. It doesn't have to be shared with ABI. No information is synced with our service or any of that. It stays within the business. Next question here, does ABI provide training? How long does the training last? Yes, we provide training as a standard with all our systems. So any purchase of any ABI equipment comes with training. So we provide training here in the UK. Where you can come and we have multiple stations that you can work with, and we can obviously be able to meet with our design team and so forth. But we can also come to you. We travel all over the world. We can provide training on site as well. And it takes about five working days, roughly, depending on the number of systems, the size of the team that we need to train. There's a pre-training program that happens online, takes place online 2 weeks before the in-person training. And then there is an implementation phase that will take between 1 to 3 months, where we would be working with your team, hand in hand, to ensure that the systems will be fully implemented. Repair Don't Waste sounds like a great initiative. How can I join the movement? Thank you for the compliment. And companies can join the movement by obviously making the investment in our solutions, attending training, getting certified, and they would benefit from not just being able to use the branding on their website, on their marketing material, like Alstom and many other companies have done in the past, and obviously potentially have articles about your company written and published on the website as well. So so get in contact with us if you'd like to discuss your requirements, so we can take this forward. What do I need to set up? A lab to start performing electronic repairs on my assets. As I mentioned at the beginning, you can go to repairdontwaste.com/learn, and you go into the workstation. There's a list there of equipment, of solutions that we would recommend. That list is evolving and it's going to continue to grow as well. But we'll be more than happy to review your needs, what you already have. If this is a brand new lab, we can advise on anything from ESD flooring to lab coats, to workstations, to rework stations, conformal coating removal equipment, or chemicals. We have a lot of expertise accumulated over the last 4 decades that we'll be more than happy to share with you. Okay, so I'm going to leave you with our contact details on the screen right now. There you go. So a big thank you from all of us here at ABI Electronics to everyone who joined us live, everyone watching this recording as well.